Basically, we're just going to continue from where we left off before. This is the section on turbochargers and engine performance metrics. So, of course, when one is working with an engine system, one has to make sure that the compressor, turbine, and so on are sized correctly for the engine of interest. So there's quite an art associated with selecting the compressor. Essentially, in order to do that, you have to know how much air the engine needs. So you have to determine what are called engine breathing lines. I'll show you that on the next slide, I guess. And then you need to know the mass flow rate through the engine, basically. So these are those engine breathing lines. Remember, we spoke about engine load and speed characterizing the engine performance. And there's a peak torque point here and a rated speed point here. Essentially, I'm plotting on this plot here the pressure ratio that would be required, the mass flow rate in the engine that would be required. These can all be estimated. The pressure ratio tells you how much air you would want in the engine. And the mass flow rate, of course, is determined also by engine speed. So these 2 points that you see here might represent the torque peak operating point, and this would be your rated speed operating point. And just by doing simple analysis, you can come up with these type of breathing lines that tell you essentially how much air you want your compressor to deliver, and therefore what the required pressure ratio would be. So those breathing lines then can be superimposed on the compressor map. So remember, we saw this map before here. This is the pressure ratio across the compressor. This is that reduced speed, the reduced mass that we spoke about. And here's your surge line, your choke line. So just to look at the numbers here, 1 is the state prior to the compressor, 2 is the state after the compressor. That's what enters the engine. 3 is the exhaust state, and 4 is the exhaust before the turbine, and then 4 is the exhaust state after the turbine. Of course, we're going to assume that the work produced by the turbine is what drives the compressor. We're going to actually introduce an efficiency here as well. That's this mechanical efficiency term. When one looks at the equations we derived earlier for the work of the turbine and the compressor and combines them, you can relate then the pressure ratio across the compressor to the pressure ratio across the turbine. P4 here is atmospheric, if you assume you're dumping to the atmosphere. P1 here is atmospheric, if you assume you're driving this as is usual. So therefore, and then, T3 and T1. T1 would be the atmospheric condition here, and T3 would be the exhaust temperature. M.F is the fuel flow rate, M.air, the air flow rate. Here's your turbine efficiency, compressor efficiency, and then a mechanical efficiency. You need to know the specific heats, obviously, because we derived this from enthalpies. They may be different for the exhaust gas and for the fresh air because you've got exhaust products here to worry about. But generally, this would be your compressor equation that you would use in the design of the system. So the plot that you see here is, again, the compressor map that we showed before. And these lines that you see superimposed here would be those breathing lines that I discussed before on the previous slide. So this would be a constant speed line here. You would determine what this line looks like by looking at the mass flow rate through the engine as a function of P2, the boost pressure. And then these would be constant load lines. And the idea is to try to get this fishing net superimposed on the other fishing net in the most optimum place, right? So remember we said that the high efficiency part of the compressor was here. So this is not a very good matching that I've shown you here. You'd want to move this whole map a little bit further up. But you've got to be very careful not to hit the surge line here or the choked line on the other side. So there's quite a bit of skill associated with matching turbochargers, compressors to an engine layout. And of course, one has a lot more flexibility if you have a multi-stage compressor system, or maybe a supercharger and a compressor, because then you're not as limited. Okay, so that's what I want to talk about in terms of just introducing turbochargers. Excuse me. Let's talk now about the ideal engine. Remember, we spoke about the external combustion engine and internal combustion engine. The ideal engine, this is that Otto cycle or external combustion engine. It looks like this. We have a minimum volume and a maximum volume. So we imagine that we take in the fresh air at the maximum volume, compress it isentropically. Then we have isochoric combustion, constant volume combustion, or energy release. In reality, in the ideal cycle, it's heat transfer from the cold to the fluid from the hot fluid. From the hot source to the working fluid. Then we have isentropic expansion and then blowdown process. So that's the ideal cycle. And if you analyze this relatively simple analysis, just looking at the thermodynamics of the energy equation, you can show that the ideal efficiency depends on the compression ratio, R sub C, and gamma, the ratio of the specific heats, as shown on this figure here. So that's the ideal Otto cycle. The ideal cycle then is just a function of these two variables, compression ratio and ratio of specific heats. If you increase the compression ratio, you increase the operating volume for compression and expansion, and that increases the efficiency. Increasing gamma increases the pressure rise during combustion and increases the work extraction in the expansion stroke. So that again increases the net efficiency. So high compression ratio engines like diesel engines have higher efficiencies, partly because of this effect. But remember that this is not the whole story, as I mentioned before. There are other factors that one has to consider. So that's what's listed here. If you look at the actual efficiencies and how they deviate from an ideal cycle, the first one is we assumed constant volume combustion. In reality, in a real engine, you have a finite duration of combustion. Although I should just point out that HCCI combustion, as we'll discuss soon, has a very short combustion duration compared to diesel or especially SI engine. But again, there's problems with that. It has to do with the very high pressures that can be that would correspond to a short combustion duration, which lead to high internal pressures, leading to noise and also high mechanical stresses in the engine. So that's assumption one. Assumption two is we don't have a perfect fluid. The specific heats decrease during the compression process because the gas temperature is increasing. So this causes a problem. It causes the gamma to vary. Also, there's the issue that the combustion gases themselves have a different composition than the reactants, again with a different gamma. So that affects the actual efficiency that you would experience. And then finally, the adiabatic assumption, which goes along with the isentropic assumption. In reality, you have very large temperature gradients near the wall because combustion is taking place in the combustion chamber. That leads to heat transfer. And so that, again, detracts from this ideal estimate. Some other assumptions, if you look at the whole engine system, so here's our engine, our intake and exhaust manifolds, intercooler, compressor, turbine. We may also have EGR, exhaust gas recirculation. So if you look in these models, you basically, in these 1D models, you'd have something for each of these components. You need a model for your compressor, your turbocharger. Typically, they assume isentropic efficiencies. So those efficiencies would be, for example, for compressors, superchargers, fixed geometry turbines, efficiencies of around 0.7. And remember that those efficiencies were multiplied together before. So 0.7 times 0.7 is roughly 0.5. So for a compressor turbine, system, typically you have about a 50% efficiency at best. Variable geometry turbines have lower efficiencies. So those are all things that have to be accounted for when one's looking at a system like this. The charge coolers, the intercooler, aftercoolers, EGR coolers, they have certain effectivenesses which again enter into the system simulation and need to be accounted for, or tuned, if you like, in models. So zero-dimensional closed cycle type analysis is very helpful when one designs an engine system. But the first thing here is really the downfall of those models, if you like, and that is that the combustion basically is just represented as an energy addition to the system. And you have to make some assumptions about how that energy is added to the working fluid. The rest of this course, we're going to talk about basically this first statement here, the combustion process. But from the point of view of a system modeler, if I tell him the combustion process, he can then use those results in his system model and account for the turbocharger system, the EGR system, exhaust gas recirculation, the entire system. So typically, these combustion processes are represented by saying that you have a certain amount of mass addition due to fuel injection, let's say in a diesel engine, with a user-specified start of injection, crank angle, and an injection duration. So why is that important? Well, during that process, you might be able to account for the vaporization process of this injected fuel and assume that the latent heat of vaporization is somehow removed from the working fluid to give you a better estimate of the temperatures in the combustion chamber, again, assuming some sort of uniform temperature in the chamber. The pressure and the mass would be integrated over the closed portion of the cycle with specified initial conditions at intake valve closure for the pressure, the temperature, and the composition of all of the species. Typically, in these system models, you might just consider relatively small number of species that represent air, let's say. And then they also assume that the post-combustion composition is determined by complete combustion. So you would ignore, for instance, CO, unburnt hydrocarbons, aldehydes, whatever may be in the exhaust, and just assume that everything in the exhaust is CO2 and water. So you don't really take into account minor species. This paper here gives a very good account of some of these zero-dimensional closed cycle models. The equations that are solved are shown here. This is now for the combustion chamber. Here's our first law of thermodynamics. Change in internal energy is due to heat transfer and PDV work, piston work. So the equations, I think I showed you something similar to this before. Here you have an expression for the rate of change of pressure with crank angle. And at a particular time in the cycle, I here, representing the particular instant in time. We have combustion related source term, heat transfer or heat loss related source term, and then the PDV work term here. So we have to somehow provide models for combustion. Typically, we use a model called a Webbe function in these zero-dimensional models. The Webbe function essentially provides this parameter x, which is the amount of fuel that has been burned. So x would be 0 when we start, x would be 1 when all the fuel is burned. It's typically assumed to be an exponential function. We have to specify the time of start of combustion and the duration of combustion. 10 to 90 here, you'll see in a minute, is the 10% to 90% combustion duration. And then there's some constants. So this Webbe function here tells you how much fuel was burned in an interval of crank angle. The amount of energy release is then related to the amount of fuel times the lower heating value of the fuel. Very simple combustion model. The wall heat transfer model, essentially we have a convective heat transfer coefficient and then effective areas, depending on what the piston configuration looks like at that time. We have the piston cross-sectional area, the difference in temperature between the gas and an assumed piston temperature, the head temperature and the area, and then the exposed part of the liner of the engine, the area and temperatures. So that would be a simple wall heat transfer model, but we need these convective heat transfer coefficients. The literature, the classic work is by Washney, which assumes that we can calculate excuse me, the heat transfer coefficient, knowing the temperatures and pressures, and then this quantity, W, which is related to the piston velocity. So higher piston velocity, it's higher convective velocities, gives you a higher convective heat transfer coefficient, which gives you more heat losses, which affects the pressure rise rate. There's a correction term here that measures the difference between the pressure and the motive pressure in the engine. So these are all built into those 1D codes. Yeah?
How do you define the Seebeck functions for different engines?
Yes, so essentially it's a correlation. You'll see, though, that people generally pick a term that looks like this for a single heat release type of combustion. For more complex heat release, where we have that premixed burn and then diffusion burn and then a late burn, you'll see sometimes a 3-part Webby function. So it's all empirical and curve fitting, basically. Again, curve fitting. But there are recommendations in the literature, and in all of those codes, the Ricardo wave, the GT power, and so on, they'll give you guidelines for selecting these constants. And there's a lot of literature on this. Okay, so what do we really want at the end of the day? We want the engine brake thermal efficiency. In other words, we want to have the most efficient engine that we can. For example, the Department of Energy has announced a goal of brake thermal efficiencies of 55%. So we've spoken about the indicated mean effective pressure. This is gross indicated work term. We've spoken about the pumping mean effective pressure, or essentially the pumping contribution to the total engine losses or gain, if this is a negative quantity. And then we have friction mean effective pressure, which is the effect of friction. If you look in the literature, you'll see that there are a number of friction models. One of them that's celebrated is the so-called Chen-Flynn model, where friction is related to the maximum pressure in the combustion chamber and the engine speed, actually quadratic function of speed. So friction increases quadratically with speed. This plot here just shows this Department of Energy goal of 55% thermal efficiency. And what I'm showing you here are these lines correspond to different values of the gross indicated efficiency that would be required if you had a pumping efficiency of 0.4 bar and or a pumping effective pressure of 0.4 bar and a friction mean effective pressure of 1 bar. These are typical numbers. You can see that in order to make 55% thermal efficiency, like this green curve here, at a particular load point, you're going to need to have about 60% thermal efficiency combustion. That's really high. And so we're going to talk more about thermal efficiencies later, but this is really a stretch goal here. As I said, if the pumping work is negative, then you can kind of get away with lower gross indicated efficiencies. But ultimately, these are the players, right? This is the pressure in the chamber, this is the pumping to get the air in and out of the engine, and then this is the friction. And ultimately, they all contribute to the brake thermal efficiency. So this is a paper that I just wanted to draw your attention to. I think it's almost, it's been accepted for publication, I think. It's from the group at Michigan. George Lavoie is the lead author on it. They looked at essentially a 1D model for engine performance analysis. It's a 90 millimeter engine, compression ratio 12:1. Here are some of the characteristics, 2 intake valves, 2 exhaust valves. The conditions they looked at was, in this case, a mid-load point 2,400 RPM, piston velocity 8 meters per second. Equivalence ratio ranging from very lean to rich combustion. Exhaust gas recirculation up to 80%. Exhaust pressures up to 3 bar, so this would be like a boost pressure if the exhaust and intake pressures were the same. Intake temperatures of 60 centigrade, which is typical. And then for the heat transfer calculation, they assumed these temperatures for the components of the engine, the head 460 Kelvin, the piston 510, and 390 for the cylinder. There's some science behind this. These numbers can be obtained from conjugate heat transfer models, which, for example, GT Power offers, or measurements of temperatures in an engine. Here's your turbocharger efficiency. They assumed several up to 60%. And here are the big assumptions about combustion, that the 10 to 90 burn was 25 crank angle degrees, and the 50% burn occurred at 10 degrees after top dead center. So I'll talk more about that in a minute, but here it just does models again. The Washney for heat transfer, the Webby for heat release, Chen Flynn for friction. We'll talk more about NOx later. Here's our turbocharger equation that I showed you earlier. Here's that Webby for the burn duration and for the heat transfer and the friction. So we've discussed those. So these are very interesting results. They plotted here gross efficiency. So this is the efficiency that's determined from the cylinder pressure from bottom dead center back to top dead center and then back down to bottom dead center. The gross efficiency doesn't include the pumping work. And it was done for a variety of scenarios. So here's the cumulative heat release that goes from 0 before combustion to whatever the final heat release was. The 50% burn point is called CA50. That's this crank angle here. The 10% burn point is here. You just burn 10% of the fuel. Here's the 90%. So the CA50 is indicated. The CA10 to 90 is the time between these two dotted lines here. So what they did in the analysis was first they assumed that the engine was adiabatic, so no heat transfer losses. So that's these sets of curves here. And each one of these corresponds to a different assumption about the 10 to 90 burn. So this first one assumes that 10 to 90 burn occurs basically instantly, 2 crank angle degrees. This last one, the 10 to 90 burn occurred in 40 degrees of crank angle. And notice that by going to a short burn duration, you see higher gross efficiencies. So each of these plots here this is the scale associated with it. The line in the middle here is the top dead center location, 10 degrees before, 10 degrees after, up to 20 degrees after. And this corresponds to the crank angle 50 location. So the first thing you note is that there's a significant penalty associated with having a long combustion duration. This is with no heat transfer. If we turn on the heat transfer, you see a big reduction in gross efficiency because now we have that heat loss term to worry about. That's the first thing you notice. Second thing you notice is that the peak efficiency is no longer at top dead center, but it's actually a little bit after top dead center. That's because of a trade-off between heat losses and late expansion. If you can keep the gases cool, you obviously reduce the heat losses, so that would be what would happen if you went past top dead center. But if you wait too late, then you lose some of the pressure, the PDV work, so there's that compromise. Other thing to note, this difference here is on the order of 10% here on this plot, or 8% or something. So that represents quite a big change in fuel efficiency because of the loss to the coolant, essentially. This plot is also very interesting. Now what we're plotting here is the equivalence ratio of the charge. In other words, going from lean mixtures to stoichiometric and beyond. Again, this is the gross efficiency here. Here is plotted the air standard efficiency for the 12 to 1 compression ratio, assuming gamma, whatever, 1.4. That would be this number here. So you can see that the efficiency decreases as you add more fuel to the engine. And the reason for that is tied up with the gamma, because as you add more fuel to the fuel-air mixture, the molecules are more complex. They can store energy internally, and that lowers your gamma. So that basically reduces your efficiency. So you're seeing two plots here. One is the adiabatic, in other words, assuming no heat loss. And the other is for different burn durations. I guess it was the black one is 2 degrees, and the blue one is for 25 degrees of burn duration. If you add in the heat loss term, you see the whole curve comes down. So you see these red curves here. The difference between them is the pumping contribution. In this example, they assumed that the intake and the exhaust had the same pressure, so the pumping work was essentially very small. So that's why there's a small difference between gross and net here. And then finally, the friction contribution is this big difference here. At light load, the friction term basically is a constant, right? The contribution then of the fuel energy becomes less and less, so the total efficiency drops, and you see this big drop off at light load. We saw that earlier when I was showing those plots of efficiency versus load. So when you're all done at the end of the day, the efficiencies are around 35% here. So that's kind of interesting. It's interesting in the sense that what we would really like is something like 63%. This is also another interesting part of the paper where they compared the difference between using lean operation by reducing the amount of fuel versus dilute combustion, where the air is replaced with recirculated exhaust products. So in this case, the equivalence ratio can be unity. In other words, you can have stoichiometric combustion. However, because of the recirculated gas fraction or residual gas fraction, which can be up to 80%, you can have an effective lean mixture. The fuel to charge equivalence ratio can be of the order of 0.2. So you can either have a low equivalence ratio by having a lot of air and a little fuel, or you can have a lot of recirculated gas products and still have a stoichiometric mixture for the amount of oxygen that's in the chamber. Interesting that if you look at the temperature, predicted burn gas temperature, someone was asking about these earlier, you see burn gas temperatures for these lean mixtures is very low, 1,000 Kelvin, and going up to on the order of 2,500 Kelvin for stoichiometric mixtures. But the differences are not that large if you have air or EGR dilution. And part of that has to do with the gammas here for the air and the EGR dilution for the unburnt and the burnt gases. So that's an interesting result from the analysis. The paper also looked at the effect of boost. I guess I'm not going to go into this here, just in the interest of time. And then I think this was the last slide one of the last slides in the paper on the combustion part, where they essentially looked at different combustion strategies. So if you look at an SI engine, like in your car, that's port fuel injected, typightly you might use a throttle to control the load, but the fuel-air equivalence ratio is unity. So it's stoichiometric spark ignition combustion. That's this green curve here, looking at brake efficiency versus load, or brake mean effective pressure. If you use late exhaust valve closing, or in this case, early exhaust valve closing, instead of throttling, you see a very similar type of result. If, on the other hand, you use stoichiometric combustion with EGR dilution, you get this blue curve here. And then finally, with air dilution, that would be the top curve. So now you're changing the equivalence ratio as a function of load. You can see that for HCCI combustion, which is essentially this black curve in this region here, you can get very efficient combustion compared to standard spark ignition combustion. So big difference in brake efficiency at light loads. However, HCCI is limited to relatively light loads, in this case around 3 to 4 bar IMEP. If you look at spark ignition engine combustion, though, typically this is operating stoichiometric or to equivalence ratios around 0.6 or 7, the lean limit for combustion. You can see that, again, if there's a drop-off here associated with changes in gamma, which reduce the brake efficiency. And then in between is what they identify as advanced combustion. So combustion that's dilute, for example, where the charge-based equivalence ratio goes from 0.4 to up to 0.6. And we're going to be spending quite a bit of time talking about this type of combustion because it's also a low-temperature combustion that has other advantages. In particular, one can reduce those heat losses, which can help you raise the brake efficiency. Okay, so to summarize our two here, turbocharging can increase engine efficiency by using the available energy that's in the exhaust and also by reducing pumping work. The ideal cycle analysis provides kind of an estimate, if you like, of engine efficiency, but there's a lot of things that it doesn't account for. Some of those 0D models can provide estimates of the system efficiency, but you need to provide combustion details and also heat loss details to be able to make realistic estimates of performance. And essentially the goal of multidimensional models is to try to predict those combustion details. And that's what we're going to talk about going forward. So hour 1 and hour 2 are basically just kind of a review of engine systems and engine performance. Now we're going to kind of get into the meat of combustion. Any questions before we do that? Okay.
One question.
Yeah.
Came up with a couple students I was talking with. You commented right at the outset of the talk about comparing an engine cycle to just a classical Carnot cycle, which is an easy thing to do. And I would guess you're still limited by Carnot efficiency by that peak temperature. And maybe you could clarify that. There was some discussion going on back here.
Yes, that is a limit. And it's kind of like an upper limit. Although, you know, if you take into account the full cycle with possibly using the exhaust energy in a turbocharger or maybe even other devices where you recoup some of that exhaust energy, then you've gone beyond that limit in a sense because you now have another way of using the available energy. So it may be a limit for the combustion process, but not for the whole system. All right? Okay. So we now want to move on to number 3, which should be here. Okay, so for this discussion, we want to talk a little bit about chemical kinetics and HCCI and spark ignition combustion. Let's see how far we can get with this. Here's a movie that we took at the Engine Research Center that compares HCCI on the left and diesel combustion on the right. You'll notice spark ignition engine combustion is still going. HCCI is very fast, and then diesel combustion is kind of in between. HCCI, as I said earlier, you assume that the chamber is homogeneously mixed with fuel and air, and then you compress it, and it ignites, kind of like a diesel engine does. The only difference is that in the diesel engine, the fuel-air mixture is not homogeneous. It is very stratified, as you can see from looking at the pictures here. Let's see if I can show that again. So these diesel jets, for example, lead to a very poorly mixed mixture of fuel and air. Looking at the diesel jets here. But they still auto-ignite, and one has then combustion taking place over a range of local equivalence ratios. So if we look at a spark ignition engine, and let's assume we have now homogeneous charge or premixed charge mixture of fuel and air, and we're going to compress it, but the fuel doesn't auto-ignite, so we have to ignite it with a spark. So that's the spark ignition engine. Basically, we have a spark plug, we deposit enough energy in the gas to get it to start burning, and eventually a flame propagates. So the question is, how does an SI engine, how is it capable of operating from 100 RPM in a ship engine to 20,000 RPM in your model airplane engine? It's a huge range of speed. And when you consider chemical kinetics, that's just one number, right? It takes a certain, at a given temperature, a certain time for conversion of fuel to products. And the explanation is turbulence. So basically, the turbulent flame speed, the flame that propagates across the combustion chamber and consumes the fuel, scales with speed. So that's just an experimental fact that explains why spark ignition engines can operate over this wide range. So if you want to model this, you have to give a little bit of thought to turbulence. We already spoke about the turbulence kinetic energy. And essentially, if you think about it, the process involved with the air passing through those valves, generating turbulence, is really driven by the piston motion. So the turbulence kinetic energy should scale with the piston speed squared. There may be a constant in front of this here. The scale of motion in the chamber is really limited by the size or dimensions of the chamber. So let's just call that L piston here. The diffusivity, or the rate with which mixing occurs in the engine, is going to be, just borrowing from the kinetic theory of gases, related to a characteristic velocity, which again is the piston velocity, and a characteristic length. If one uses the K epsilon model, you can relate that to K squared and epsilon. Epsilon itself, the dissipation rate, follows an expression something like this. If you take the ratio of K and epsilon, K over epsilon, you get a time scale, which is basically the piston dimensions or the engine dimension divided by the piston velocity. So this is a basic time scale for combustion in an engine. Some years ago, Professor Bracco and I proposed a model for engine combustion where we said the rate of change of species concentration is driven by the local value of species mass fraction, let's say, or concentration, and the equilibrium value. So this rate expression has the advantage that when you reach thermodynamic equilibrium, the conversion stops. The rate of conversion, tau c here, we argued depends on the turbulent mixing timescales. Okay, so that's a basic idea, and the consequence of that is pretty profound, because let's say we look at this little plot here of temperature versus distance. We have higher temperature on the burnt gas side, lower temperature on the unburnt gas side, and we have a propagating wave. So you don't need to know much. You can go back to the 1890s or whenever Millard Le Chatelier did their work, and you can show that the propagation speed of a front depends on diffusivity or diffusion coefficient and a reaction rate. So if you plug in this diffusivity and this reaction rate, which essentially is this time scale, what you find is that the flame speed, the turbulent flame speed, depends on the piston velocity. And so this model can explain this fact here. Now, yeah.
Is the chemistry time scale incorporated in tau c?
So this is the point of my discussion here. The assumption is that you have a flame. Okay, now you can only have a flame if you have chemistry going on. But ultimately, the thing that controls the combustion process is the rate with which you mix the burnt and the unburnt gas. So I've prepared a special slide to show that. I'll show it in 1 second. Let me just come to this one first, and then I'll combine the two. So for diesels, we have this situation. We inject the fuel into the combustion chamber. I'm showing you just one spray plume here. At a certain moment, we get ignition. Well, here's the injection crank angle, in this case 18 degrees before top dead center, which is over there. And it just sits and cooks for a while. During that cooking process, we create radical species, we create intermediate quasi-steady species or stable species, and eventually at a certain point it all goes off and we get a big increase in temperature. That corresponds to the ignition. So in the early days there was a lot of work done where the so-called shell ignition model was used, where basically you have your fuel, hydrogen abstraction creating radicals, then the formation of these intermediate species, branching species, and labile intermediate species. This guy here is very important because this is the one that essentially controlled the ignition delay, the formation of this cube here. Once it reaches a certain value, ignition takes place and combustion occurs. So if you look at this from the point of view of modeling, you'd have to describe your ignition delay. And once ignition occurs, again, you can switch to a characteristic time type combustion model where the fuel itself is then converted to products at a rate that's now determined by the timescales associated with the injection process. So now the injected nozzle diameter and the nozzle or the injected fluid velocity become the turbulence generating agency because of this very high velocity spray. So again, you can use the same type of characteristic time combustion model for diesel and for spark ignition models. So in response to your question earlier, this kind of summarizes what goes on. Here's your spark ignition engine. It's the mixing of the burnt gases and the unburnt gases that brings the burnt gases up to a temperature at which ignition is going to take place in a spark ignition flame front, a traveling wave flame front. The time scale of this mixing is determined by essentially parameters related to the engine size and the piston velocity. Piston velocity determines the turbulence intensity, if you like. And here's a plot from previous CEFRC presentation that shows the turbulent flame speed divided by the laminar flame speed against the turbulent fluctuating velocity and the laminar flame speed. So basically, a linear plot here shows that the turbulent flame speed is proportional to the fluctuating velocity in the turbulence. And that we already saw is proportional to the piston velocity. Of course, you see there's a whole lot of scatter around here. So this is just the first overview of combustion. So that's what happens in a spark ignition engine. We're basically relying on the mixing time scale to mix burned and unburned fuel to create the conditions appropriate for flame propagation. In a diesel engine, the appropriate mixing now is the fuel being mixed with the air. So we inject the fuel. This entrains air, and it's the mixing of the fuel in the air that essentially sets off the combustion process. So basically, it's again a mixing process, but now the time scale, as I said, is due to the injection process. Yeah?
Are we more moving towards now direct injection, and therefore dealing with these same kind of mixing issues?
Absolutely. Yeah, and in fact, we'll be talking more about that.
So one more question.
Yeah.
What role does gas expansion play in increasing that burning velocity? Because
so that's
case,
definitely an issue because these now are high temperature gases that expand, so you see an effective faster flame propagation.
Because just the ratio of the turbulent to the laminar is just a couple of tenths.
Right, and that's probably part of the reason for some of this scatter here. Yeah, thanks. Okay, so if we just summarize then, where are we? We've got gasoline spark ignition engines that have flame propagation. What do you want for that to work in an efficient way? You want high turbulence so that the flame speed is high. So that means you need some kind of special arrangement with your ports. You want some way of generating swirl and so on. The problem is, though, that with high turbulence, you have high heat losses. So that reduces your efficiency. The other thing is that behind the flame here, you have very high temperatures, and that leads to high NOx and unburned hydrocarbons, and CO can appear ahead of the flame if your flame doesn't propagate all the way across the combustion chamber. You don't burn all the fuel. So those are issues with the spark ignition engine. Fortunately for the spark ignition community, Somebody invented the three-way catalyst back in the 70s. And so they can deal with these things here. They can eliminate NOx, unburned hydrocarbon, and CO. But that, of course, is wasted energy, right, if you're throwing away unburned fuel. So that's another reason why thermal efficiencies are low for spark ignition engines. You also have throttling losses because in order to maintain stoichiometric combustion and still have load control, you have to basically lower the pressure in the chamber, throttle the gases, and there's losses associated with that, as we saw. The other thing is that these engines are limited because of knock, so they can really only operate with low compression, relatively low compression ratios compared to diesels. And again, there's a lot of sensitivity to the fuel, as you know, because you have to buy 3 different types of fuel at the gas station, right, depending on what kind of engine you have. Diesel engines, on the other hand, have spray combustion. So essentially, these red regions that you see here are the location of the flame. The temperatures are high. This can lead to high NOx. And then inside the flame, you have very rich fuel regions, which lead to particulates or soot. So aside from these problems, the thermal efficiency is higher because you don't have the throttling losses. The load is controlled by how much fuel you inject into the engine. Okay, so those are diesel and gasoline. Now, if you look at homogeneous charge compression ignition, this is a low temperature combustion strategy. Basically, the combustion is controlled by chemical kinetics. That makes it very sensitive to the fuel that you use. So for example, here I'm showing a plot of in-cylinder temperature versus crank angle. I'm assuming I have a homogeneous mixture here in my combustion chamber, and so I can just plot one temperature here. I have my compression process, and then because for certain fuels, such as diesel, it's actually a 2-stage ignition process, I have some heat release, and then it sits and cooks some more. And then I get a 2nd stage combustion. But because of this initial heat release, the 2nd stage combustion occurs much earlier than it does for a fuel that has only single-stage combustion, like gasoline. So again, depending on what type of fuel I use, my combustion phasing can be completely different, which leads to this fuel sensitivity. The other thing is that we have poor load control, because if all of this fuel goes off at the same time, there's no way of delaying the combustion. I get pretty much a vertical line over here, which leads to very high in-cylinder pressures. That means I can only operate at light loads. One advantage, though, is because I have a very well-mixed combustion situation and I'm operating at low loads, I get low temperatures, which means low nitric oxide, and there's no rich regions, so I don't get soot. That's the big appeal of HCCI. Okay, so for modeling premixed charge combustion, and let's say HCCI combustion, the equations that we discussed earlier become quite a bit simpler. For example, these are our mass conservation equations for the various species. We only have to worry about the time term and the combustion source term. All of the terms involving spatial gradients we can throw out. There's no spray term, so that goes out. So in each of these computational cells in my domain here, I just have to solve these ordinary differential equations. Along with them are these equations governing energy conservation that we spoke about before. Again, I just have the time term and the combustion term. Don't have to worry about any of the other gradient-driven terms. So this equation then looks like this. You've seen this already, I'm sure, in many of your combustion classes. Basically, we have an equation for the rate of change of species mass fraction for the NS species. That's driven by this term QK here, which is the difference between forward and backward rates once we specify a system of reactions. In this case, we have NR reactions. And then the stoichiometric coefficients for each of the reactions are shown here. W is the molecular mass for each of the species. Typically, these reaction rates are in the form of Arrhenius functions. And the energy equation essentially keeps track of the energy release as I consume species, the associated energy that corresponds to that species. So you've seen these equations. I don't have to spend time on them. Okay, so now we're done, right? Well, no, because the problem is we need a chemical kinetic mechanism. And as you've seen, you've probably seen this plot before as well, these mechanisms can be huge. This shows number of reactions versus number of species up to a C9 no-name type of compound here. You can see we're talking about 10,000 reactions and many thousands of species. If you try to solve this in a CFD code, you'll be running for a year, right? Because there's a tremendous amount of overhead associated with the chemistry. In fact, for practical engine simulations, we're really limited to about 100 species. We need to be able to predict these delay times, ignition delay times, and combustion accurately. So that means we really need reduced mechanisms. A lot of work has been done in that area. This becomes really significant when you look at even larger molecules, all the way up to like C18 and so on, or biofuels. So I don't know if I need to spend much time on this because you've seen a lot of the hydrocarbon kinetics in your other courses. But basically, if you look at the shell model that we discussed earlier, or this basic path here, you start from fuel, produce intermediate species, which then lead to ketone type species or isomerization steps that correspond to the low temperature branching. So here's temperature, here's ignition delay time, if you like. This acceleration or reduction in ignition delay time is due to these low temperature steps. As the temperature increases, though, another path becomes more important, and that's the olefin path here, which essentially takes over from this. And eventually, when the temperatures are high enough, then we see, again, the hydrogen-oxygen combustion taking over, leading to the high temperature combustion. So Marco Mel at Lawrence Livermore put together this plot which just sort of summarizes that for an HCCI combustion. Here you have cylinder pressure or temperature shown here. The blue region corresponds to the low temperature branching paths with aldehydes and ketones. The orange region here is the negative temperature coefficient region where the ethers and olefins become important. And then the hydrogen combustion steps for the fast high temperature. Okay, so next few slides, and I'm just looking at the clock there. Let's see. We're finishing at what time did we say? 12:15, right?
12:15.
Okay, I think I have a bit of time here. Next few slides talk about mechanism reduction. And back in the 2004 era, when we started trying to integrate detailed chemistry into CFD codes, we spent a fair amount of time looking at available mechanisms in the literature. And one of them was the Lawrence Livermore N-heptane mechanism. And if you, which is many steps, as I'll show you later, in many species, if you look at all the reactions, you can essentially identify reactions that are most important qualitatively. So for example, looking at temperature versus time, this is now for a constant volume ignition delay calculation. What you find is that reactions 1 and 7, which correspond to essentially the H atom abstraction and the formation of those isomers and ketone steps, this reaction and this one, control the first stage ignition delay. The amount of heat that's liberated during that period, that first stage combustion, it really depends on the breakdown of this ketone species to formaldehydes. So that's this area you see here. Then reactions 3, 4, and 5, which essentially boil down to producing hydrogen peroxide, control the second stage delay. And then finally, the second stage ignition process when you have sufficient hydrogen peroxide accumulated. And then finally, the last stage here is the CO plus OH reaction, which leads to the energy release, or a significant amount of the energy release. So basically, this type of profile that you see here corresponds very well with experimental data. So this is data here from Viehweger, it's a shock tube ignition delay Here's again the temperature profile that I just described to you with the first stage and second stage combustion, the heat release associated with that. And you only need those 7 or so reactions to be able to catch all of these features. And in fact, that's what the Shell model did originally. You can sort of relate the Q species in the Shell model to the hydrogen peroxide and so on. And the formaldehyde to the branching agents. If you look at the ignition delay versus 1 over temperature, you've seen these plots a lot, I'm sure. You can see the negative temperature coefficient region here. This is for the second stage ignition, and this plot down here shows the first stage ignition. So one can model this entire type of experimental data with a relatively simple model. And that's described in this reference that you see here. However, when you go to more complex chemistry, you need some other tools. And I guess tonight we're going to hear about the DRG method. But anyway, there are many methods of mechanism reduction. One of them that Young-Chul Ra has looked at a lot is something he cooked up, which I think is actually pretty intuitive. For all of the reactions in the mechanism, you can essentially take the pre-exponential and multiply by a factor, say 2 or half, and see what happens to the ignition delay curve. So here's ignition delay versus inverse temperature, or temperature in this case, sorry. And you can see that by changing this rate coefficient, you see significant changes in the predicted ignition delay. So if you have experimental data, you can match the experimental data by appropriate choice of that constant. Well, here he's looking at just one reaction, peroxide going to the keto species for a tetradecane mechanism. So he identified what he calls ignition delay sensitivity coefficient. Essentially look at how much the delay time changes here as a function of temperature. You can plot that on this plot here as your ignition delay sensitivity versus temperature. And what you find is, as you can see with your eye, is that it's high in this region, but at high temperatures, that particular reaction doesn't play much of a role. Well, we already saw that, right? These keto reactions are low temperature reactions. But anyway, this plot here allows you to identify the temperature range over which that particular type of reaction would be important. The other thing that he looked at was what he calls a delay gradient sensitivity coefficient. So you look at the change of ignition delay with respect to temperature, and here's his parameter. And what he identifies here is this can be positive or negative depending on the reaction step itself. If it's positive, this curve here tends to rotate in a clockwise rotation, and if it's negative, the curve tends to rotate in a negative orientation. So that's a very useful metric because you can basically list for all of the reactions in your system these sensitivity coefficients. And that's, for instance, done here and described in this paper, where we're looking at 9 very important classes of reaction in hydrocarbon kinetics here, and dividing the delay, the ignition delay versus temperature plot into these 3 zones corresponding to low temperature combustion, the negative temperature combustion regime, and then high temperature combustion. The green arrows show essentially the effect of the sensitivity coefficient. So a dark circle here and an arrow down means that I can, by increasing the rate of this, I can pull that curve down in region A. Here in region B, or C rather, it would pull it up, and so on. So for each of these reaction classes, you can identify what effect they have on this ignition delay curve. Again, the point of this exercise is that if I'm given an ignition delay curve like this from experiments for some fuel for which chemistry may not necessarily be very well understood, but I can kind of represent that fuel through this classic set of classes of reaction, I can match that data using this strategy. So the sensitivity ignition delay curves for heptane shown over here, solid circle, open circle, and blank means dominant, mild, or not significant influence, and then the counterclockwise or clockwise rotation effects of each of the reaction steps. So here you see that applied, for instance, in what we call the Engine Research Center multi-chem primary reference fuel mechanism for N-heptane and isooctane. We started from the Lawrence Livermore N-heptane, 560 species, 857 species isooctane, and the ERC N-heptane mechanism, and combine all of this together to produce a 41 species mechanism for PRF. As you can see, it does a pretty good job. Here's the ignition delay versus experimental data for N-heptane air, and here for isooctane air, and here for various isooctane N-heptane blends. And you can see we can match experimental data over wide ranges. So this PRF mechanism I'll be referring to quite a bit later in the lectures here. It's kind of our base mechanism at the Engine Research Center for modeling a variety of different fuels. However, we're more interested also in more general fuels. So for example, I'm going to be talking about vaporization processes next when we meet tomorrow. We're going to have try to have fidelity in matching the distillation curves and the properties of the fuels. We're going to have physical property surrogates that represent the cycloalkanes, the N-alkanes, the isoalkanes, aromatics, and also biofuels and so on. So those will be the physical properties, and that's relatively easy to identify because many of these species are well characterized in the literature. Their physical properties are well characterized. The chemistry, on the other hand, is not that well characterized, and particularly when you get to very large molecules. So what we've done is to make the argument, and this I think is something that Charlie Westbrook and others have also indicated is not too bad an assumption, is that when a molecule becomes essentially large enough, you can represent its combustion chemistry by using a relatively simple surrogate. So for example, for the cycloalkanes, we use cyclohexane as being a chemistry class, if you like. And that's great because the Lawrence Livermore group has a 1,000-something species mechanism for cyclohexane, which, using our tools, we've reduced to a 67 species mechanism. Similarly, for, say, the isoalkanes, we represent them with isooctane. We take the isooctane mechanism of Lawrence Livermore and reduce it to a 25 species mechanism. Aromatics we represent with toluene, same type of thing, and ultimately create a mechanism that consists of roughly 100 species and can cover a wide class of fuel types. This just shows a little bit of some of the results. This is applying this multi-chem mechanism to propane, N-heptane, isooctane, toluene, methyl cyclohexane, decalin, and matching with experimental data. We actually have at this time, a little more than this, but when this was written, N-heptane, isooctane, tetradecane, cyclohexane, decalin, ethanol, the methyl butanoate, decanoate fuels, all in the multichem. So talking of the biofuels, there's a lot of interest in America in soy-based biofuels. Biodiesel consists of these 5 components here, primarily. What we do is we model the saturated components with the methyl decanoate mechanism from Lawrence Livermore, 3,300 species roughly. And then for the unsaturated components, we use methyl decanoate mechanism. And so to represent a fuel like this, we would have essentially the N-heptane plus methyl decanoate, which gives us a C18 type of molecule. And then for the unsaturated, again, N-heptane with the decanoate. So the fuel itself might consist of a certain amount of palmitate, stearate, and so on. And so this is how we break it up and represent that fuel. We're able to model that with just 85 additional species, but this includes some of the species that are already in the multichem mechanism. So when we were all done, I think it brought us up to 120 species total. And we're able to match the Lawrence Livermore mechanism with the multichem data. Okay, so to validate these mechanisms, obviously we're interested in engines, not shock tubes. So we also want to apply these to engine data. We're fortunate to have data from Sandia. Here's a paper that describes some very careful experiments done by John Deck at Sandia, where he measured cylinder pressure versus crank angle for a variety of premixed mixtures of fuel and air. In this case, isooctane with various equivalence ratios as shown here. This is what the engine geometry looks like. It's a relatively simple piston geometry. We account for the crevice, the piston liner crevice region here. And you've seen this at bottom dead center. Fairly coarse mesh, 2,000 cells. But remember, this is homogeneous, right? So really the only important cells are the ones near the walls. And you can see we match that data very well, the experiment and the calculation. Here's some more HCCI data from our group running on a Caterpillar truck type engine, gasoline HCCI. Here we have different cases with different engine speed, different equivalence ratios, different intake temperatures, and very early injection of gasoline to create a homogeneous mixture in the combustion chamber. And you can see cylinder pressure versus crank angle, and then these curves are the heat release curves derived from the cylinder pressure. Very good agreement between the experiment and the simulation using our, in this case, isooctane mechanism. So the other thing that has happened recently, and this is going to allow bigger mechanisms to be included into CFD codes, is the use of sort of strategies to speed up the chemistry part of the solver. One of them is adaptive multigrid chemistry, or AMC. The idea here is that if you take a part of the combustion chamber and do some testing and find that all of these cells have roughly the same temperature and equivalence ratio, instead of going to call your chemistry solver for each of these cells, you can group them all together and then go off, say, with your solver like ChemKin, solve this whole group at one time, and then take your results and remap it back to the cells. And in the process of remapping, you want to make sure that you conserve mass, obviously, number of carbon atoms, number of hydrogen atoms, and oxygen atoms. And there are techniques to do that that are described in our book here. The other approach that also saves significant computer time, especially for very large mechanisms, is to dynamically determine the mechanism size based on local and instantaneous thermal conditions. So for example, when you're late in the combustion process, and most of those ketones and the intermediate species are no longer even present because they've all been consumed, why carry them in your mechanism? Get rid of them. And therefore, you can reduce the size of the mechanism from 3,000 species down to 1,000 or whatever it is. So significant savings is possible. And that's described in Long Liang's paper. This just shows an example of a calculation that we did with a relatively small mechanism, the ERC-PRF mechanism here, looking at cylinder pressure versus crank angle for an engine combustion case, using the full chemistry with this, as I say, relatively small mechanism. Took about 2 days on this particular calculation, HCCI. With the adaptive multigrid chemistry, since it's HCCI, a lot of cells look similar to their neighbors, so that reduces the computer time by an order of magnitude by introducing that simplification. And then, in this case, the dynamic adjustment of the reaction mechanism size gave a further improvement, but obviously not as large as you would see if you had a huge mechanism. So, those are things that are out there, and people are starting to do calculations with species in that number close to 1,000 instead of 100. Okay, so I want to switch a little bit gears here and talk about now, again, premixed charge combustion. So we've got a homogeneous mixture of fuel and air in the chamber. But now we're going to spark ignite it instead of compression ignite. And in this case, we're going to have to model flame propagation. The approach that we've used in Wisconsin is to modify our Kiva simulation, this Kiva code that we use, to include the so-called G equation. The G equation essentially allows you to track the location of an interface, which in our case is the flame. And we're going to couple that with a detailed chemistry solver. So basically, the turbulent flame propagation problem will be solved by monitoring the location of the flame with the G equation. This allows you to consider both laminar and turbulent flame speeds, as I'll discuss. And essentially, it's the primary heat release calculation. That's where most of the energy release occurs across the flame. The model also allows for flame quench when you have mixture stratification. Behind the flame, we have the post-flame chemistry. So here we can have our detailed mechanisms working to monitor the CO oxidation, the slow oxidation steps, nitric oxide, and pollution formation mechanisms. And ahead of the flame, we then again have our detailed chemistry operating to predict auto-ignition potentially, and this might lead to knocking combustion. So that's the flame propagation model that we're currently using. How does this work? Well, basically, here's our spark plug. We use what we call a discrete particle ignition model. Now, why do we need that? A spark gap is typically very small, 10 thousandths of an inch, much smaller than the computational cell size in an engine. And the growth of that initial spark kernel cannot be resolved on a practical mesh. So we use a particle approach, and I'll tell you more about it a couple of slides from now, where the particles represent the growing flame kernel. When they reach a size that's big enough, we then transfer to the G equation solution, and that's this equation down here. So what we're calculating is this parameter G, which is, as you'll see in a minute, arranged so that the burnt gas has G greater than 0 and unburnt gas has G less than 0. What does that mean?
This transfer coefficient, this is the molecular transfer coefficient.
You got the wrong slide up there.
Yeah, but I said here,
Is that me again? Okay.
Is that in anything on your computer?
No, it looks like it's doing okay on the computer. Thanks. Okay, sorry for the break there. So the G equation is shown down here. It's just a transport equation, a time term, a convective term. But on the right-hand side, we have this interesting term. It's driven by the turbulent flame speed. So we're going to need to feed that into this model in order to calculate the propagation of this wave. Things like the gas expansion effect is included here because we include the density in the G model. So just to show a picture, this is a two-stroke engine that was modeled. In this case, we actually have direct injection of a spray and then the ignition. Now you see this circle that you see here. These are the ignition particles that I mentioned before. We just left them in the picture here. But basically, once the kernel reaches a certain size, we switch to the G model and then calculate the flame propagation. So look at that one more time. There's spray, ignition, and then combustion. You notice the combustion doesn't go all the way to the walls here because we have actually a lean quench occurring in parts of the chamber. The G model, as I said, allows you to keep track of the interface between the unburnt fuel and the burnt fuel. It actually applies over the whole range of equivalence ratios from rich combustion to rich to lean combustion. And behind the flame, we can have diffusion processes occurring. So basically, all modes of combustion are possible with this strategy. G is the location of the G surface is determined by this turbulent flame speed and the propagation process of the G equation itself, determined by the G equation itself. Okay, just a word about flames in turbulent flames. Here's a plot that some of you may have seen before from Norbert Peter's book, where he describes the regimes of combustion that occur in a spark ignition engine, for instance. Here's our turbulence intensity normalized by the laminar flame speed. Here's the turbulent length scale normalized by the laminar flame thickness. And as you can see, there are regimes that go from just having a laminar flame that is wrinkled by the turbulence all the way to the turbulence breaking up the flame and essentially quenching the flame. And typical engines operate in a range here that are characterized by flamelets. So basically you have laminar flames that are propagating into this mixture, but they are all contorted and have very high surface areas. So the surface area that corresponds to the fuel air to products conversion process is much increased by the fact that these flames are corrugated and these thin reaction zones combine to form a turbulent flame. So one of the important questions is to determine what is the flame thickness in an engine, like a laminar flame thickness. And you can estimate that from Maillard-Le Chatelier theory. It turns out to be about 20 microns. That's the thickness of a laminar flame under engine conditions. So Professor Gandhi in our group has developed some really amazing measurement capabilities, and recently made some measurements of the Kolmogorov scale of turbulence in an operating engine as a function of crank angle. And what he found was that the smallest scales of turbulence are reached around top dead center and are also about 20 microns in thickness. So basically, the smallest scales of turbulence are already bigger than or comparable to the flame thickness, which is, I think, very interesting. But it has another very important consequence. And that is that it's not possible to resolve a turbulent flame on a practical engine simulation grid. So if you think about an engine, it's 10 centimeters in diameter, let's say a truck engine. If you have a reasonable number of computational cells, you'll find that the cell sizes are on the order of a millimeter. Whereas for flames to be resolved, we need tens of microns. So there's about a 2 order of magnitude discrepancy between size of the cells and the flame thickness. So it basically means that we need a model for turbulent flames. We cannot model them from first principles in engines. All right, so here are these models. Norbert Peters has a model that describes the turbulent flame speed as a function of all kinds of parameters here. The important ones are U prime, the turbulent intensity. Remember we said that under certain conditions, the turbulent flame speed becomes proportional to the turbulence intensity. The other parameters here, this is tau, is our time scale for the turbulence. This term here is actually a term that is 0 when you're at just close to the ignition time. And so the turbulent flame is actually propagating at the laminar flame speed right off the bat. So that's where our kernel model starts. We have ignition occurring. We have all these particles that represent the location of the flame. They move out at a velocity that's given by roughly the laminar flame speed. And then this term becomes bigger and bigger, and eventually we transfer to the turbulent flame velocity. So this transition between particles and the G model, which is shown again down here, occurs when the size of this kernel becomes comparable to the turbulence length scales in the engine. So you can read some of the details in these references for how this is done. The other thing you need is the laminar flame speed. You can calculate this if you have a mechanism, but generally you rely also on experimental data here. Here's a paper that is a sort of classic paper in the field that describes how the laminar flame speed changes with temperature, pressure, and dilution, or EGR. We have used this model. What we found was that it doesn't adequately represent the rich or lean limits, so we modified that ourselves and found that to be useful. I think I'll skip this here. The last thing I want to show you is just a bit of validation. Here we have a port fuel injected engine. Next time, tomorrow I guess, I'll talk about the direct injection version of this engine. It's an 89 millimeter bore, 79 millimeter stroke, 12:1 compression ratio, spark ignition engine, 1500 RPM. We're going to look at port fuel injection with spark timings of minus 44, that's 44 degrees before top dead center, up to 32 degrees. It's throttled, so the manifold pressure is 65 kPa. Remember, atmospheric is 101, right? So we throttled. And we're going to look at operation of this engine. So here you can see a picture of the domain. It's a pent roof engine with 4 valves. You can see that here. Here's at 20 degrees before top dead center, I guess for the case where we spark timed 20 degrees earlier than that. Here's the initial G surface. The spark plug is located in the middle of the chamber here. You can see it at 5 degrees before top dead center. The flame is propagated quite a distance. Here's at 10, here's at 20. And if I'm lucky, I'll be able to show you a movie of that. So we see the ignition and the development of the combustion. I'll show that again. Okay, so I stopped it here just so, well, maybe I should go a little further. So, I lost it. I wanted to show you those. There we go. The spark kernel particles as we transition from spark ignition to the G model. And then finally, here are some validation results from engine experiments described in this paper here. Cylinder pressure versus crank angle for the different spark timings. You see very nice agreement over a wide range of operating conditions. These models are now used widely, and also this work was funded by Ford, so they use this a lot for their engine design. Final thing I want to talk about is, okay, we spoke about how flame propagation is important in a spark ignition engine. What if we turn off that G model and we just simply use chemical kinetics to determine the combustion process? Well, that's shown here, cylinder pressure versus crank angle. Here you see the experimental data in blue. The G model I just showed you is in red here. But if we turn off flame propagation, basically what we find is that we're just not able to calculate the proper fuel to products conversion rate. I'm going to show you results with the direct injected engine later next time. But the difference is not so large here because, and somebody asked about this earlier, here you have fuel injection also aiding the mixing of the fuel in the air. But here this is premixed. And without a turbulent flame propagation model, you're just not able to capture the correct flame speed. Remember the Maillard-Le Chatelier result. So if you just compare what happens in cylinder, here we see that spark kernel at early times, they look very similar. But now you see very slow combustion if you're just using kinetics-controlled combustion versus with the G equation. So basically, to summarize R3 here, the most important takeaway is auto-ignition chemistry is not sufficient to properly model flame propagation. The turbulence-enhancing effect of flame propagation speed in SI engines cannot be neglected. And that's one of the reasons why modeling SI engines is a real challenge, because basically you have to know how the turbulence interacts with the propagating flame. So I think it's 10 past. I think we may have time for a couple of questions, and then we have to run and have a photo taken. Yeah.
You have been using the G equation with the detailed chemistry.
Right, right.
But the G equation models a flame surface, right? It's a flame sheet approximation.
Right. I skipped that slide. And the cell that contains the flame it assumes that you go from unburnt fuel to burnt fuel following the characteristic time type combustion model that I spoke about earlier. But outside of those cells, everything follows the chemistry, the chemical kinetics model, combustion model. Yeah, there's some details in a slide that I skipped if you want to take a look at that.
There's one question. Over 10 years ago, John Day showed that in a practical spray, the ignition was taking place at very high equivalence ratio locations.
Right.
But most of the chemical kinetics which are developed they don't go for very high equivalence ratio for validations. Can you comment on that?
It's a problem. Yeah, we'll talk more about that later also when we talk about direct injection. Yeah.
Thank you for the lecture. Your reduction of a mechanism, my experience is that you can achieve a very compact mechanism when you only aim at predicting the auto-ignition delay. When you want to capture the laminar burning velocity, then it becomes very inefficient.
Right.
And you have to add species there. So I'm wondering how much.
Yeah, so here
consideration
we're
is
not
given
really
to that.
calculating laminar flame velocities. We're
Right.
relying on somebody to give us those.
Okay.
But you could get that from a detailed mechanism if you trusted it, or experiments. Or,
Okay.
yeah.
With respect to the AMC approach, it's very similar to the reactor network approach. I wanted to ask you, well, at least that's what I
Yeah.
understand, how is the diffusion flux between the cells calculated, especially for the extended dynamic chemistry?
Yeah.
You eliminate some species.
Yeah, so there's a lot of details that I guess I'm going to refer you to the papers there. But basically with the AMC model, you only pick cells that are within a certain constraint, like maybe 10 Kelvin close to each other, before you group them together. And in that way, you try to make the argument that they're similar. If you widen that range, then you'd have to account for diffusion between groups of cells, and that's not accounted for in that model. Yeah.
So it's similar to this question about reduction. So when you're using the G equation, you said that in a cell that has a flame, you're using chemistry. So is that the chemistry from the reduction using emission play, or is that full chemistry?
So we never use the full chemistry in the CFD calculation. You can't afford to do it.
Right.
Yeah.
But it's just that
So there would be reduced mechanisms.
but it's reduced using the ignition delay as the
Yeah, basically, yeah. You want to make sure at least you track ignition delay in your reduced mechanism. Yeah.
But even though this problem is not calculating the flame with the G equation, so it shouldn't be different chemistry.
Okay, so the propagating flame is handled with the specified turbulent flame speed.
Okay.
All right. It's the knock ahead of the flame, knocking processes, and so on. That's where auto-ignition chemistry is important. Yeah. We'll talk about that as well. Okay, one more. Yeah.
This is related to mechanism reduction again. So do you have a special strategy for keeping pollutant precursors and soot precursors in the radiation chemistry?
Absolutely. And in fact, we have PAH, reduced mechanisms for PAH that allow us to get some fidelity in soot precursors up to pyrene, and that's an area we're currently working on very heavily. Yeah. Okay, we probably should run because it's 1:15. We'll have time for more questions tomorrow, I guess.